Okay, student, to complete the chapter 1, we're going to go through the new example 1.3. In this example, as you can see, the core here is contained of three legs, 1, 2, 3, and we have two windings. This is the first one, and the other one. As you can see, the left-hand side is totally the winding is totally different. In the case of the turn direction, totally different with the right-hand side. But the interesting things is whatever this winding goes down is connected to the other side. So since 10 amps is goes in, 10 amps must be comes out. This is for this. The ratio N1 and N2 exactly the same, 500 turns, and the value of the core is given by here. You can see this leg 2 centimeter, 2 centimeter, 2 centimeter, all three, and the other side also 2 centimeter by here. If you see, where is my pen? Just I need the pen. Okay, draw 2 centimeter by here and 2 centimeter by here. Between these two, we have 50. So the average length from this, if you can remember in the face-to-face class, the first one, I mentioned we should calculate the average length. So from BAFE, we have one side, which is one leg. So since here is 1 plus 50 plus 1, so 52. From here, from this point to this point is also 52. You can see 52, 2 is 52, the average one. Since this point, which is F to E, also 52. So we can mention the length L of core in the side of B AFE, BAFE is equal 52 times 3, correct? Times 10 minus 2. Convert centimeter to meter. So LC, the core length for BAFE is exactly the same for the other side, which is BCDF. So it's equal to length of BCDF, correct? The last part of the core we have to analyze is from B to E, which you can see. Okay, B to E is only 52, is upon 50 right here. 1, 1, 52. So the length of B to E is equal 52 centimeter minus the air gap, which is 0.5. So the total is 51.5 centimeter. And length of the gap exactly is equal 0.5. We have to convert this one. It means this is shouldn't be here. Times 10 minus 2 meter. For this one is times 10 minus 2 meter. Correct? Yes. Okay, if I'm going to represent the magnetic circuit in the form of electrical circuit, we have to convert this part to a voltage source, which we call it MMF, or magnetomotive force number 1. Using the right hand, the fingers, all fingers except the thumb, on direction of the current, the thumb will give you the direction of the flux. So you can find out, we can represent it as a positive, negative, correct? MMF, MMF1, which is 500 times 10, N times I. Can you remember MMF? It was Ni, correct? So it is 5,000 ampere turn. 5000 ampere turn. Then we should have a reluctance, which is reluctance, or should be such this one, reluctance, this one, BAFE. So the reluctance BAFE. Then we have two reluctance in series. This is BE, correct? BE, yes. And the other one is RG. The other side in the same way, we have a reluctance. Name is BCDE. BCDE. Then we have a source, still not sure about the direction, and then finish. That's all we have. These two also connected, okay? So it means this is connected. So in the case of the other one, again, all four fingers except the thumbs in the direction of the current, then the thumbs will give you the direction. So positive, negative, this is MMF2 in the same value of MMF1, which is 5000. Then let me find another color. Here, flux number one will, sorry, this is flux number two, and this is the flux number one. So it is very clear that we should find out anything here in this way using KCL. Is it? Yes. So let me see. What is the question by here? It said that relative permeability is given 1200. Neglect the leaking and fringing effect. All dimensions are in centimeter, and the magnetic material has square cross-sectional. Oh, another things by this square cross-sectional I can understand is A. What is A value here? Because if I zoom in, you can see two, assume this is cross-section I want, okay? So it's 2, 2, and then in direction of X, sorry, in direction of Z, we also have another, which is depths. So 2, or we should consider it as a 2D. If it's 2D, so 2 times 2, 2 times 2 times 10 minus 4, okay, which is 4 times 10 minus 4 centimeter, correct? So this is the A by here. Then what else? Determine the air gap flux. So they ask what is the flux by here, phi g. Then air gap flux density. Oh, they ask for phi g. Then after that you can easily bg and then hg, correct? Yes, hg. Okay, what is the value here? Step one, we should find out the phi g. How we can find out the phi g? The phi g is very clear. The phi g is here. So what is the value of phi g here? Phi g, phi g here is equal phi 1 plus phi 2, correct? Yes, okay. No, another things I can distinguish from this circuit is since the circuit is identical, so reluctance BAFE is equal reluctance BCDE. Okay, so reluctance formula is given by length, which is 52 times 3, 10 minus 2. 52 times 3, 10 minus 2. This is reluctance for these two. Okay. L over mu. Mu is mu 0. Mu 0 is a constant value. Can you find anywhere easily? Then mu r. Mu r is given by here 1200. 1200 times A, which is 4 times 10 minus 4. This is one of the reluctance. So the other reluctance, so this value must be calculated, okay, easily. Next step is the reluctance of the RBE. In the same way, we know the length, which is only 52 times 10 minus 2. The other things, I think the denominator the same, which is mu 0 1000 4 times 1200 mu 0 times 4 times 10 minus 4. Lastly, we should calculate the RG, which is 0.5 centimeter, which we return it to meter, 10 minus 2, mu 0 only times A is 4 times 10 minus 2. No, sorry, minus 4, correct? 4 minus, yeah, correct. So these are the values we know. Then what should we do? So we can calculate all this value. Then we should write down the two parallel equation at the same time. From this source is 5,000, which is MMF number 1. Let me clear here. Then change the color to blue, I think. So MMF number 1 is equal RBAFE, reluctance BAFE times phi 1, correct? Up to here, plus RBE plus RG, which are in series connection. Then times what? Times phi 1 plus phi 2. And the other equation, this is for the left-hand side. For the right-hand side, in the same way, MMF2, RBCDE, and the middle branch exactly the same. So MMF2, its reluctance R BC DE phi 2 plus R means reluctance BE plus R G times phi 1 plus phi 2, which is phi G. Phi 1 plus phi 2, correct? So since here you can calculate everything, means we know the values, which values we know. Of course, we have phi 1, phi 2, this one we have, this one we have. We have all the reluctance except phi 1 and phi 2, okay? So you can calculate it, two equations, two unknown. Easily you can calculate the phi 1 and phi 2 using your calculator or using any other software, means MATLAB or maybe online one, up to you. So by the next slide, you can see they calculate this one, correct? Yeah, RBAFG are the same as something I mentioned. Oops, sorry. The reluctance calculated. Then, yeah, here, let me change the direction of this one, okay? Here you can find out the phi 1 and phi 2 calculated as I mentioned, okay? As I mentioned by here, both calculated. So phi 1, of course, is equal to phi 2. The value is given by here. So when we know the phi 1 and phi 2, we can calculate the phi g, which is phi 1 plus phi 2. You can see by here, phi 1 plus phi 2 is 5g. And the value is given. Then because we're talking about the air gap, let me clear this screen. Delete. How can I delete this one? I think I have to select whole page first, then delete it. Okay. Clear screen. Then, okay. As we know the 5G, okay, 5G, what color is this one? It's very ridiculous. Okay, we know phi g Okay, and we know the formula phi equal BA, correct? Then BG and AG. So AG is exactly the same as other A because said it is a square. Okay, so A is 4 times 10 minus 4. B unknown. The G also the phi also known as here. This is the value for. So the B, which is flux density, is 1.034 Tesla. And H, as we know, B equal mu H, and here is mu 0 times mu R. So mu R is 1200, mu 0 is known. B also known. H can be calculated from this point easily. So if I change this one to the other side and oops, maximize this one, you can see B or mu 0. So mu R, of course, is not there. Sorry, it's wrong, of course, because we are calculating for the gap. So no need to considering the mu R, correct? So the value is given by here. Okay, next is calculating the inductance. Okay, in the case of calculation of inductance, we can calculate the inductance in the way that any coil or any toroid will produce inductance in the system. Okay, because mm, it is related to flux linkage. So what is a flux linkage? Flux linkage are usually showed by lambda equal n times phi. So n, what is n? N is number of turn. So you can see n phi is number of turn. Phi is the flux, correct? So we know n and phi. Finally, L, which is inductance, is lambda over I. I is the current of this coil. So represented as n times phi over I. How we can represent phi? Phi is BA, correct? So let's represent the phi as a BA. So it's n BA over I. Then again, we know B equal mu H. So let's n on behalf of B, we can write down mu H A times, over I, correct? Then how we can represent I? We know from MMF formula, HL equal NI equal R phi, correct? So I is H times L over N. So we can just H times L over N. So we can move this one from denominator to the top side, which become N2, correct? So I remove this one from here. Then H and H can be cancelled from the side. And then this top mu and A can be go down to the denominator side. So these two cancel by here and here. Why the color is such a this crazy? And then become mu A. So can you remember what's the meaning of L, which is L mu A? Yes, correct. It is reluctance. So you can see N2 in numerator and reluctance in denominator. So L can be represented as N power of 2, number of turn, by power of 2 over reluctance. As simple as this one. You can calculate and find out the meaning of the inductance in the system. So let's calculate inductance in this system as example to learn how it's work. Okay, magnet is circuit. This circuit given number of turn is 400 turns. Mean core length is given as a 50 centimeter, and the air gap also is given as a 1 millimeter. Very good. Cross sectional also for the air gap and the coil is given as a 15 centimeter square centimeter, correct? For the core, relative permeability is given as 3000 and the current is only 1 amp. So the question is, find out the flux and the flux density in the air gap. Okay, what is the phi? How we should start? The same as previous case, we can easily start in this way. So we need to calculate phi. Step 1, phi is calculated from MMF Ni equal R phi equal HL, correct? So N, we know the number of turn 400. I also given 1 amp, correct? Phi is unknown. We want to consider the phi. We don't know the phi times reluctance. So reluctance can be calculated here. So reluctance here is equal L over mu over A. But we have two reluctance in series. One is the core reluctance. The other one is air gap reluctance. So for the core reluctance, it is 50 centimeter. So it is times 10 minus 2 over A also is given 15 centimeter times 10 minus 4 times mu, which is 3000 times mu 0, correct? And this is RC, our core, and R gap is calculated in the same way, but a different value, of course. It's on behalf of 15, I have 1 millimeter. So it's 10 minus 3, correct? 15 times 10 minus 4 times mu 0. Then these two connected in series S, so they must add to each other. Then we can find out the reluctance and find out the phi and find out the flux density, which is B. We know phi equal BA. Then for the next part, inductance, L equal, based on the last formula, N power of 2 over reluctance. Which reluctance? Total reluctance. So you can see RC first is calculated, the same as something I wrote by here. RG also, then the total value of RC and RG considered, or a denominator, and NI at numerator, and finally the phi is not calculated by here. It's here. 0.6463 times 10 minus 4, and then divided by the A, following this formula, and the value for the B, which is flux density, is 0.4309 Tesla, and the L also calculated in the same way, N2 over RG, which the value is given by here. Okay, so hope you understand the meaning of the connection. I suggest you to calculate and solve this one using HL, because you can also calculate H in the same way. And you must understand in this circuit, the phi is constant, okay? So the B is constant, but H is not constant, okay? Be aware of that one. B is constant for all the circuit. If phi is constant, okay, B is constant, but H changes. And this one is the meaning of reluctance also changes, okay? Next step, hysteresis and losses. Okay, I think I explained this one before in the simple word, okay? Hysteresis is exactly related to BH graph. As you can see by here, let me zoom in. You can see we have a coil, we have a toroid, and we have somehow a windings around that one. That coil, that coil is energized by a current, which is a AC current. You can see we have a positive side, negative side, and again repeated can be repeated. Okay, going and back. So if we inject this current to this point, what is the result? Okay, you can see here the result is given, but is really strange maybe for you. The BH graph before that wasn't the same as this one, correct? That one previously I shown the same as this one. This is what BH. This is the other BH. Where is the other BH graph? This one. And the others in the previous slide, you can see this one. This is called static pH graph. And this one, the new one, is called dynamic. So what is the difference? The difference is not a, somehow a meaningful one in the case, but you should understand the procedure, how the dynamic created, okay? Let me zoom in and explaining from the point. Oops, okay. Assume 0 here is this point. When the coil and the toroid and the core are not energized, okay? And I should say these haven't energized ever. These two, this system, up to now, never energized, okay? Then when we inject positive current, okay, the magnetizing increase, can you remember, is increase in this way, then reach to saturation point. Then it reached to saturation point. Where is this saturation point? This saturation point is here. See? This saturation point, the first one coming here. Okay, it reached its saturation point. Okay. Then, based on my expectation before, as I was a student, when we return back from here to 0, we should return back from the same line to the 0 point. But because of the different domain, we cannot return back on the same way. Let me give you an example. Assume you're coming to the university early morning, okay? Are you going back to home exactly on the same way? No, of course. It's a bit different, yes? So if you considering you coming to the school, university, okay, on the same way and returning back exactly on the same way, we can set, okay, we can following the new green light I just plot, okay. Otherwise the difference is something look like this one. In the return pass, when from maximum we're returning to the 0 point, we reach from this point, let me show you the new green. We coming back from this point to this point, okay. So this is this 0. Then, again, let me change it to the other color. Since this 0, the current become negative until the maximum negative point. We return, we're going down until this point and reach to this value. Again, the same procedure, but in the vice happen. So we are going up. From here, we should go up. So new points comes out. We're going up and then we reach to this point. Again, if you repeat it times to times, many times, okay, you will find out different type of graph, but more or less all of them in this area. So finally, we said the dynamic BH graph is something look like this. purple color. I try my best to redraw. Okay, so changing the domain affected the BH graph. Okay, and what is the result of this one? The result of this one is losses. So we have lots of losses in the power system because of the we call it hysteresis losses. Hysteresis losses can be calculated by this formula. The losses equal to KH, which is the KH is somehow a constant value. I think it's given between 1.5 to 2.5. Then B max, B max, the maximum flux density, power of N, when the N, oh, sorry, this value is for the N. The value for the N is between 1.5 to 2.5. KH must be given, different machine, different value, and F is the frequency. So if this is given to you, you can calculate the losses of the hysteresis. So hysteresis losses produce heat inside the core. So they are not welcome, but this phenomenon is available in all machine and is avoidable. We cannot remove it from the machine. So next losses in the machine, it's called eddy current. Eddy current. These losses are quite interesting, and the engineer tried their best to avoid, but still exist in the circuit. Okay, can you remember? We should go back to the first part of the of this unit. Can you remember I mentioned when we have a current in a wire using the right hand side, then this is the way the fire start to circulate, correct? Yes, start to circulate in the around the wire. Okay, now if we have a core, iron core, you can see this is the iron core. It's a bit bigger than a wire, correct? So the phi is here, so easily can rotate and make eddy current inside this one. So the eddy current start to rotate start to rotate here, 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 here because of the phi. So this rotation is some of the losses, and this one can produce again the core of the transformer, electrical or other electrical machine hot, and these are the unwanted losses. Again, these losses cannot be avoided, but the engineer make the core of the transformer and electrical machine in lamination. I think by the next session, week 4, which is next session face to face, I try my best to present the transformer coil and the electrical machine coil in DC to you to see how the laminations are. And another one, to avoid this one, they can add somehow another material to the core for high resistivity. So if you have high resistivity, this circulation can be avoided and reduced. Finally, you can find out the value of eddy current by Kc B power of 2 frequency power of 2. This one, the difference is the value of K, which is different from previous one. This is KH. B max power of 2, previous one B max power of N, and frequency here is power of 2. That one is power without any power. Okay, so we have two losses inside the core which cannot be avoided. Remember these two. This is a good question for the final or somehow the exam, for me to ask you and ask you to explain how they created, how we can avoid that one, and how you can explain. Okay, I think we reached the final stage. Yeah. Okay. We reached to very interesting part of this unit, which is we're talking about Faraday law. Faraday's law is the most important, still is the most important in my view, and It is the one we use in the electrical generator to explain how we generate electricity. Okay, assume the phi is phi max sine omega t. So it means that our phi inside the machine is changing with time. So the phi is changing with time is equal phi max is changed in a sine form omega t, which omega is 2 pi f, correct? 2 pi f. F is frequency of our system. In Malaysia, frequency is 50 hertz. Don't forget that one, okay? 50 hertz. So we call this one angular frequency, and F is a frequency. So how the voltage injected to the other side, or how the voltage create the real voltage, this voltage you can see using in this wall, it's E potential, which is changing by time, or you can call it Vt. Okay, we usually call it Et here. It's N. What is N? Is the number of turn in the coil. D phi, the changes of phi over dt over time. Okay, then we can calculate d phi over dt using the formula, because the phi is here. So phi max sine omega t. If we using the formula, calculating that one is n is here coming down. So phi max also is there without changing. So sine omega t, omega coming out, correct? On behalf of sine, we should having the cosine, the cos omega t. So Emax here, Emax here, it's all this value n, phi max, and omega. It is very clear that phi and voltage, so the flux and voltage are not in the same phase with each other. You can see the phi started from 0, but the voltage is 90-degree lag. 90-degree lag from the phi is very important. Don't forget that one. Later I will explain more about this one. So what is the voltage? The voltage we use, how we call it, 230 or 240 or 220, whatever you call it, okay? The voltage you use, how we call it? It is VRMS. So here we call it ERMS. No worries, later we change it to VRMS, okay? This is based on the Faraday's law, okay? So Emax, what was Emax? Emax is here. Emax cosine cos omega t. So it's n phi omega something. Okay, over square 2. So if we put the this Emax over square 2, you can change the phi to 2 pi f. So 2 pi over square 2, this value comes out. So on the other way, we can set the voltage is somehow equal 4.444 n n frequency phi max. Okay, this is how the Faraday's law working. So here again in another way represented. Faraday law is basis of transformer operation. Transformer operation, also using that one, state that the flux passes through a turn of a coil of wire. A voltage will be induced on the in the turn of wire that is directly proportional to the rate of the change in the flux with respect to time. So in the Faraday law, the time plays the most important part of equation. Okay, last last example here. We have a single phase 120 60 hertz supply, which is connected to the coil. Uh, I think I missed the figure. The coil 200 turns with 200 turns. The parameters of the core are given as length of the core is 100 centimeter, cross-sectional area also given, and the mu are also given. Obtain and express the flux density in the core. Obtain and express for the current in the coil. So for this idea, we should consider and calculate the Faraday law in the case of the uh, phi max. Okay, phi max here is 120. How 120 is comes? What is 120? Is the voltage. Okay, you can see phi max is here. ERMS, can you remember ERMS? I think this voltages is related to Europe. So the voltage in Europe is 120 and the frequency 110, 120, and the frequency is 60 hertz. So you can see 4.44 times n, which is the number of turn times the frequency. The phi is calculated by here, so phi is BA. Can you remember phi equal to BA times A? So the A given by here, 20 square centimeter, and then the B calculated by here. In the next part, they call how we can find out the current. Based on the formula, we know H, sorry, B, we can B over mu, correct? So the mu is mu times mu. This is mu r times mu 0, and this is the value for B max, correct? Then I max can be calculated from MMF formula. In MMF formula, it's HL equal Ni. So the values considered by here. And then you can see again current. You can see current and V are in the same phase. Okay, that's all for this chapter. So for by the victory, I think we can cover whole tutorial number 1. Thank you very much. Thank you.